So, quick announcements. Reminder again, quiz 4 is due this Friday. Please remember to start considering design a question. I saw one pop up on Piazza already. Good job. Whoever posted that, you are evil. So definitely, this is an opportunity to start to put together questions that will make it onto the midterm. One other quick announcement. There's a conference coming up. If you're interested in this point, this is a conference for girls in STEM hosted on March 28th. There's a series of keynotes in this part. It's a really good way to connect with the community. If you're interested, this is something that, again, definitely support. Another good way to sort of see what's going on in the area and also to keep connected to some of the other investments and other things here on campus. So last class, we talked our way through enamines. This is the other nucleophile that sort of matches the enolate portfolio. Remember, we've walked our way through using these carbon-centered nucleophiles, taking these carbonyl compounds and then turning that alpha center into a carbanion. Then we worked through sort of stabilization. These are things like the malonate or malonic ester synthesis, as well as acetoacetate. Last of these enamines. These are neutral versions, these nucleophilic compounds, following the strategy that I can take a normal carbonyl, convert it into a better nucleophile, and then continue it on as we go through. We are done talking about these alpha, beta, and saturated compounds, talking about these nucleophile-electrophile pairings. So we're going to jump over now to chapter 15 in Volhard. That's chapter 21 in Brown. One quick update. We have gone through and corrected or added other practice problems to the suggested practice problems. So those are now updated online. So if you go to the other points, there's textbook questions we've sort of highlighted and broke out. What we're going to talk about now is pivoting away to this area known as aromaticity. This is talking about benzene, talking about Hückel's rule and anti-aromaticity. So these are some things that you guys have seen before. This is now diving into this where we're actually focusing on aromaticity as a class. There's kind of two things we're going to do from this. Is one, how do we use it to our advantage? What happens when we form it? So we're making molecules that will be aromatic, but also we're going to be using that to actually decorate compounds. So we're going to be functionalizing benzenes. Today we're mainly going to focus on introducing reactions specifically with phenol. It's a bridge over to the enolate chemistry we've been talking about. So phenol, remember, is a benzene with an OH onto it. I'll show you guys how that's both sort of like an oxygen type nucleophile, but we can also use it almost like an enolate type reactivity. So going back, you guys know benzene. Benzene is one of the first sort of basic sort of ones we teach when we talk about aromatic compounds. Even though we draw it like this is the introduction we usually give you for things like resonance, right? When we talk about a molecule like this, the hybridization, if you look around this point, each of those carbons is sp2 hybridized. And that's easy to look at this from a decomposition. Each of them has a single pi bond and 3 sigma bonds. So that matches sort of the sort of hybridization canonical definition of sp2. Now, what makes them different, right, is even though we're drawing them as this alternating double single, each of these bond lengths is identical. Even though you know normal, right? A single bond would typically be a bit longer, double bond is typically shorter. The idea here we're showing is the problem we have with our normal Lewis dot sort of structure is it doesn't properly represent the reality of what's going on here. It's not truly that we've got this short bond, long bond, short bond, and they are not bouncing back and forth between these two. This isn't two equilibrium isomers you can freeze out. This is an average definition that's just taking advantage of the fact that we don't have a great way of describing using this canonical sort of 8-electron Lewis dot type structure of what's really happening here, which is actually a sharing of pi electrons around the entire system. This is actually, you know, the story behind this, if you go back through and people are trying to solve this idea of benzene and then breaking out this concept, it was the other sort of versions and structures of benzene were actually kind of wacky when you look at them now. But it's really this breakout to say that resonance is really what's happening, that the conjugation in the system, or this conjugate pi electrons, are actually part of a much larger molecular orbital shared about the entire part. And what that just means is that there's really no diagnostic difference. Each CH on this molecule is identical. Each CC bond is identical, despite the sort of representation we sit here. Now, common names. These are molecules that what we're doing is derivatizing the benzene. You'll commonly see these and probably have interacted with many of them. So off the top, does anybody recognize one of these? Where have you maybe bumped into something like benzaldehyde? Has anybody played with benzaldehyde, been able to interact with it? What does it smell like? Yeah. You made it in Chem 245? Benzaldehyde, yeah. What did it smell like? It's like maraschino cherries, right? It's kind of a, well, if you did it right, it should be. So, what you'll notice, molecules like benzaldehyde or nitrobenzene, both of them have sort of this sweet, kind of cherry-like smell. And that's partly a representation of, remember, these molecules, part of them, they're called aromatic because they do have some very diagnostic and specific smells. But both of these guys here have that sort of common one. Again, this is actually a part that's in those components. It's a scenting agent. Toluene, does anybody know toluene? Where may you interact with it day and day? It's a common solvent. Does anybody have made model airplanes? Oh God, you guys, yeah, I know kids don't do that anymore. It's a plastic glue typically. Toluene ends up being something that's used to actually fuse together. It's very commonly used as a solvent in things like paints and other kind of adhesives and stuff too. Very, very diagnostic smell. The reason I say that is I used to have a student that was like, oh man, I love working in lab. I love the smell of toluene. The actual answer is, no, you like getting high. That's not the smell of toluene. Benzoic acid, very common, right? This is the oxidation product of benzaldehyde. If you oxidize benzaldehyde, you go up to benzoic acid. So these are all molecules you've interacted with in different pieces. In particular, phenol, you probably, if anybody's smelled phenol, it smells very antiseptic. It smells like something that you'd actually have, and it actually was used as a cleaner. You can actually use it to actually polish down and disinfect surfaces too, because it does act as an antiseptic agent. Now, for all these compounds, the common names, when we have one thing on a group, we give it this kind of name that's based on the functional group that gives it partly back to where it was discovered or its property in some cases. But when we have two things on a ring, now you have to start designating the relative orientation of these components. So, first of all, the parent molecule, two methyl groups on a benzene ring, is called xylene. That's the name we give it. But there are three different isomers of xylene. What we call O, M, and P, which stands for ortho, meta, and para. Ortho is just saying that the two groups that we're talking about are in the 1-2 position relative to each other. Now, because remember, benzene is a circle, what it allows us to do is start anywhere on this ring with our numbering sequence. So typically by convention, if we have two groups, what we're going to do is start off by giving one of those groups priority as number 1, and we count around the ring to give us the lowest number relative to direction. So this is not 1 and 6, it's 1 and 2 because it allows us to go through whatever rotation to give us the lowest numbering component. This would be 1 and 3 because we're counting in this direction. This is 1 and 4. Again, doesn't matter which way you go around, you get the same component. But that substitution pattern is important because each of these has actually very different properties. How you make them is different, their stabilities are different. They are isomers of each other, so they have different things like boiling points, freezing points. The colligative properties are different. Now, we're going to come back to this repeatedly. This positioning is going to be what we're going to use as a selectivity component. If we want to decorate a ring, where that first and second group is something we're going to have under our control. Now, stepping back, broadly, arenes, right? These are molecules with like aromatic hydrocarbons. Again, we mentioned this thing because they're typically very volatile. They have like lower boiling points. And a lot of times they're classified by very distinctive odors. So again, back to what I was mentioning before, things like phenol, things like benzaldehyde, they're very, very typical. In fact, when I was an undergrad, I remember we had a lab in second year where the goal of it was to classify which molecules were in a mixture. So they would hand you a sample, and your job was to take it apart, isolate each component, and characterize them by IR, NMR, things like that. And I remember watching my professor come through at that time, and he sniffed the vial, and he's like, oh yeah, that's ortho, no, para. And I'm like, you have an NMR? Like, this is the moment that I thought that organic chemists, as you get older, they're like vampires. The longer you live, the more powers you gain or something. But it's experience. Like, basically, if you worked around this enough, it is something that sort of does kind of, it's something you learn just based on this exposure, and your scent is actually a very, very critical one to that point. So all of these molecules are what we call aromatic. Now, aromaticity is something that's based on what was called Hückel's rule. Here you had a molecule where we knew the structure, 6 carbons, 6 hydrogens, but what was special about it is it had this inert reactivity. We knew the composition. We knew it's like, double bonds and single bonds. But what seemed really strange is, even though you had a molecule with this kind of, I'm 3 double bonds and 3 single bonds, it was way, way, way more resistant to reactions than the linear molecule if you had those same 3 double bonds, 3 single bonds stretched out. Somehow, they didn't burn it the same way. They didn't oxidize with simple things. If you treated them with reactions that would normally take out a double bond, like reductions with hydrogen and palladium, it didn't seem to care about benzene. So there's something that was based into it, and this aromaticity is what we kind of gave it this name to. It's a special stabilization that only happens if certain rules are met. So Hückel's rule, in order to be aromatic, you must meet these 4 criteria. Number 1, you must be cyclic. This is important because what we're doing is we're creating a molecular orbital of resonance where the start and end of it, all those pi bonds need to share with each other. It's not just a linear thing. Linear is good, resonance is okay, but this is a much higher degree of stabilization than just resonance alone, so it's one step further. Cyclic is really important because this gives you the ability for all electrons, all pi electrons, to be related to each other. Next, you can't have unhybridized p orbitals you have to have at least one unhybridized p orbital around the ring. What I mean is, what you're doing is sharing a pi bond across the system. Since pi bonds are made from this pp overlap, every carbon or every atom that's part of this ring orientation needs to reserve at least one p orbital in order to participate in this resonance structure. As soon as we are devoid of that, as soon as there's a p orbital that's not available because we've had to hybridize it in a different way, you break aromaticity. It has to be planar. That's another key thing too, because remember the geometry of your pi bond. A pi bond is created by taking 2 carbons, you have your p orbital, and it's that sideways overlap between the 2. There's a geometric restriction. If I take 2 sp2 carbons and I line them up in this plane, that's how I form my pi bond. If I do this, where the 2 p orbitals are now orthogonal to each other, I've effectively twisted or broken that bond. So planarity is important in order to have this delocalization. Last is this count, this 4n plus 2. What we're saying is that if I have a certain arrangement of atoms, they all have p orbitals, they're all linear. Now what I have to do is start populating those atomic orbitals and those molecular orbitals, and it just works out that the 4n plus 2 rule means that you fully filled all the bonding relationships without putting electrons into the anti-bonding relationships. So these are the 4 things we have to go through. The hardest one usually is this. Counting the number of electrons that are in your ring are probably the hardest thing for sort of visual representation. That's the part we're going to practice a little bit too. The other ones should be easy by inspection, if it's cyclic or not. So let's look at these. Take a moment. I want you each to sort of discuss this one out and sort them out. Which rules, remember you got your 4 rules. Do all of these meet those rules? Which rules are being broken as you go through this part? So take a second and rank them as, is it aromatic or not, based on the 4 rules I just gave you. What's that?
Is this right so far, or?
I think so. Okay. Let's start off with this one. So let's count them off these. Do you have a cycle somewhere in this molecule? Yeah, we got cyclic, right? So that's possible. Specifically, the cycle we're talking about is this chunk here, right? So this exocyclic part, we don't consider it. That's outside the ring. Is it part of things like resonance structures? Maybe. but it's not part of the cycle. The cycle is specifically this cyclic chunk right here. So that's kind of X outside that part. Is it planar? That's where it gets tricky. Remember, go back to one of the first rules. This one here, saying that they all have to have at least one unhybridized p orbital. What that's really saying is, what is the hybridization of the atoms in this molecule as drawn? Okay, so everybody, and again, creepy chant, I'm going to point to centers, and I would like you to tell me SP, SP2, or SP3. So this one, this one, this one, this one, this is fun, this one, this one, that's your problem, right? If it's sp3, in order to have the bonding you see there, the hydrogens in particular, I have to have 2 hydrogens, which means that carbon is spending every one of its valence orbitals in order to do bonding. I'm using up all of my p orbitals because that is an sp3 center, which means I have 4 sp3 orbitals. There's not an unhybridized p available. Remember, this guy here, if it's sp2, what that means is I have 3 times sp2 orbitals and 1 nice, ready-to-go p orbital. That's my content. That last one with the 2 hydrogens, it's sp3. There's no p orbitals. I can't use it. Think of it like an insulator. There's no way I can draw a resonance structure that has a double bond over here, because that would have to break one of those hydrogens, right? As drawn, this is not aromatic. Can't fuck. Okay, next. Is this guy aromatic? That one's easy. Why? Straight line. Doesn't work. Hybridization. Is this aromatic? Okay, question. Is it one big aromatic thing, or is it 2 aromatic things? It's actually 2. So look at it this way. I am a ring. Check. Each center is sp2. Check. Remember the 4n plus 2 rule. 4n plus 2, remember, what we're saying is the number of pi electrons we're looking for is 4n plus 2, which means if n equals 1, I'm looking for 6. If n equals 2, it's 10, right? N equals 3 is 14. If this was one big thing, how many pi electrons would I have to be considering total? Well, count in the bottom ring. The one I just did down here, how many pi electrons are my contained in just that bubble right there? Right? 6. There are 2 per double bond. There's a total of 6 in that part, which means just down here, I satisfy my 4n plus 2 rule. There are 6 electrons in a benzene ring. Cool. That also means up here, I have another, how many? 6. If this is all one big bucket, I should have 12. That does not follow my rule over here, right? I'm looking at 6, 10, or 14. 12 is actually what we call anti-aromatic. It violates one of those rules, flying too close to the sun. What it just means is you have 1, 2 aromatic regions. And if you actually look at this, this is what we call biphenyl. Biphenyl is actually twisted. If you actually look at this molecule, it does not sit planar because, look at it this way. I'm a hydrogen, I'm a hydrogen, I'm a hydrogen, I'm a hydrogen, nom, nom, nom. They're bumping into each other, right? So making it planar is actually very, very difficult. So because that means the bond in between the two of them is more like just a sigma bond. That cross-conjugation, actually lining them up, is a bad thing. We use that for reactivity, but the way this molecule sits is it's 2 plates that rotate against each other, where those hydrogens actually bump into each other. Fun fact for 3rd year, that makes this chiral. It becomes a twist axis. It's what we call atropisomerism. It's not actually a point chirality like RNS. It becomes a rotational axis. Fun for another day. What about this guy? Aromatic or not? So is it a cycle? Everybody in the ring has an sp2 or a pi electron or a pi orbital ready? Yeah, that passes. How many electrons? So that counts. That's up here. 18 electrons. That's an aromatic molecule. And it does turn out to be planar. It's big enough that it looks like a sheet of graphene, right? And this is where they kind of can stay out of each other's way. So we're going to go through these ones later after the point, but same thing. It's going through this game of looking at your number of centers, your cyclic component, and then actually doing your count. So if we're just dealing with carbon, hydrogen, counting the pi electrons is a little bit easy because all we have to do is find a double bond. If you have a double bond that's part of this ring system, it counts as 2 electrons. The question comes into hybridization around centers that have things like lone pairs. So something like pyridine, we've seen this guy before. Let's go through this component. Is it aromatic? So, is it cyclic? Yeah. Does every atom in there have a p orbital that allows us to do this delocalization? The answer is yes. And again, these ones we can do quickly. sp2, 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 all the way around. What's the hybridization of that nitrogen? Is it sp3, sp2, or sp? As drawn, right? It is a nitrogen with 1 pi bond. It is sp2 hybridized. This, as it's drawn here, is simply sp2 hybridized. And again, if we're going to do that count, we're saying an atom has a single pi bond. If you can see a pi bond drawn to it, it means it has to keep a p orbital available to do this. This pi bond here is only possible because the nitrogen is holding back one of those things. It just means the lone pair is in what orbital? It's the sp2 orbital. So what we have here, the decomposition, this is an sp2 nitrogen. These electrons are in a p orbital. These electrons, well, there's a different color. These electrons here are in an sp2 hybrid orbital. It's like it's in one of the sigma orbitals. The 2 carbon sigmas, those are sp2 hybrid. The lone pair is stacked in the sp2 hybrid orbital. It means geometry, it's sitting out, pointing away from the ring. That lone pair is not part of the resonance. It's actually just available out into the space. It's basically like what should have been a hydrogen, but pointing out into space. Okay, let's do, for fun, thiophene. Let me do the 3 again. Is it a ring? Yes. How many pi electrons do we have here? Visibly, you see 2 and 4. So the question is, remember, lone pairs, this sulfur has 2 lone pairs. The question we're coming to is, do I have 6 electrons in this whole ring? Basically, are those lone pairs part of your resonance structure? Or do you have 8 electrons? Are both of them in here at the same time? Part of that also comes down to what's the hybridization. Around the ring, each of these carbons is going to be sp2. So what's the hybridization of that sulfur? sp, sp2, or sp3? It's sp2. Remember the rule we taught in first year. If I have a lone pair, and that lone pair creates a pi bond in at least one resonance structure, you have to reserve a p orbital so that that resonance structure could exist. What I mean is, let's redraw this. The resonance structure here would come from taking, let's say, that lone pair. If I donate it down, I would draw it like this. If I bumped all my electrons over, I'm using the lone pair and the sulfur temporarily to form a pi bond adjacent to it. That's going to look like sulfur, double bond, double bond. That's going to give sulfur what charge? Positive or negative? Yeah, positive charge. And we've now dumped an electron pair over here. There's still a hydrogen. And there's an electron pair chilling out over here. It's a negative one. That's a valid resonance structure. It's ionic. It's going to be higher in energy, yes. But you can form this, which means that sulfur can have a pi bond associated with it. One of those electrons, the one that I've drawn in pink, these electrons here sit in a p orbital. The green ones, you would say, sits in an sp2 orbital. What we're saying is that they're differentiated, right? It's the geometry at that center means there's one lone pair. The sulfur green lone pair is kind of pyridine-like. It's sitting orthogonal to the ring. It's sticking out into space. It's acting like a sigma bond. The red one you can think of as that one is delocalized. It's part of an aromatic ring. It's part of a pi bond. Yep.
Does it matter that it has a bigger pi orbital, so there's not a good overlap with the carbon?
So yeah, what you're talking there is, since the sulfur is a bigger orbital, what we're really talking about that is that the relative stability of that resonance structure may not be as good as, let's say, nitrogen, right? What you actually see because of that is, yes, thiophene is aromatic, but it's going to be a little bit more reactive. It doesn't get quite as much stabilization as something like furan would. So the orthogonal one here, what you're talking about is sulfur versus oxygen. Both of them have that same property, two lone pairs. They are both aromatic. Furan will be more aromatic just because it has a higher or better sort of overlap in that capacity. But yes, they both count, right? You'll see that coming out in sort of the reactivity later. But does this make sense? This is the first thing that you guys have to be able to do is look at these heteroatoms, look at an aromatic ring, and then decide, is that lone pair in either a p orbital, meaning that it is part of some pi bond somewhere in a resonance structure that may not be drawn yet, or it never is part of a p orbital. So for example, imidazole here, we've got a lone pair there and a lone pair here. Green lone pair. Is it an sp2 orbital or a p orbital? All loud together, it is in pyridine-like, yeah. Because this nitrogen already has a pi bond, it's in the sp2 orbital. This one here, sp2 or p? P orbital. In order for the molecule to be aromatic, in order for that nitrogen at the top to actually be part of a resonance structure, I need to buy in with my pink lone pair. I need to reserve it in a p orbital so that it can be part of resonance structures. So that's where they designate. Because of that, what you get is different reactivities. The sp2 lone pairs, you can use them for certain reactions because they don't mean that I have to borrow or break the aromaticity. If I did something that took this lone pair and formed a bond with it, yes, I've bonded to that lone pair. Yes, I made a nitrogen plus, but I actually did something even worse. I stole that lone pair that was available to do hybrid bonding, to make this pi bond exist, to do the resonance structure. Effectively, I've removed the ability for this molecule to be aromatic. This is why it changes reactivities. Yes? Yeah? Yes, both of these nitrogens are sp2 hybridized. So two different ones. Both nitrogens in this molecule are sp2 hybridized. Excuse me. So both nitrogens are sp2 hybridized. The green lone pair down here, because of the bonding, that lone pair is in the sp2 orbital, not in the p orbital. The red or the pink lone pair up here at the top, that one is in the p orbital, not sp2. Look at the bond content. Down here, this lower nitrogen has a sigma bond to carbon, a sigma bond to carbon, and a lone pair in an sp2 orbital. That's the content for my sp2 centers. On the top one, I have a hydrogen, carbon, carbon. All of my sp2 sigmas are taken up, bounded to different centers. That means the lone pair is the one that's going to be left back in the p orbital. Right? Very good. Okay, so I want you guys to work through this point too. I'll do it in the example after, but you should be able to take molecules like this and do this decomposition. Really what we're asking you to do is take a molecule you see here and then do the resonance structures. Yes? Yes, yes. All these guys, every one of these guys is aromatic. Sorry, apologies. They all have 6 electrons, each one of them. They all are going to be planar. Every one of the guys you see up here are all aromatic heterocycles. Yes? Okay, so this is the one that I'm going to ask you guys to work through. These guys are nitrogenous bases that you see in DNA. So how do you actually go through these ones? Identify them. Where are the orbitals or where the lone pairs sitting in terms of their geometry. You're focusing mainly on the ones in the ring, but you should be able to do that assignment for even things like the lone pairs on the oxygens. So, class 1, aromatic compounds. Aromatic compounds have those 4 things. They are cyclic, they are planar, they have 4n+2, and everybody has a p orbital, right? Much like, does anybody know the story of Icarus? You flew too close to the sun? That's much worse than trying at all. That's the same thing as anti-aromaticity. So aromatic means if you make those 4 things, if you do all 4, well, you gain massive extra stabilization. Having an aromatic molecule means it's not just the same as a bunch of double bonds. This is a very stable molecule that gets a special stabilization because of it. If you try really hard to be aromatic but screw up one thing, you pay the price. This is why we call them anti-aromatic, because the number one is this part here. if the molecule is almost aromatic, but you violate the 4n rule, like it's not 4n plus 2, if it's just 4n, what you get is molecules that are actually unusually unstable. They actually are way more reactive than you would normally run into. And again, this kind of comes down to what I was talking about the molecular orbitals. What's happening here, why you get this stabilization, is you're taking all of those p orbitals. Remember, when you combine them together, atomic orbitals being combined together makes molecular orbitals. That's the sort of the buckets that you can put those electrons into. If we have those molecular orbitals, all molecular orbitals can exist just because you've combined them together. Which orbitals get populated are the ones that change the reactivity of a system. In other words, if I have 4n plus 2, what I'm doing is I'm populating all of the bonding orbitals and none of the anti-bonding orbitals. As soon as I do this, basically instead of just 4n plus 2, with 4n, that count means I'm populating several of the anti-bonding orbitals as well. I'm actually fracturing the carbon-carbon bond as a result of it. So these guys right here all end up becoming what we call anti-aromatic. They almost act like two unpaired electrons in a diradical, because again, what you've done is dumped in electrons into an antibonding orbital, which just means they don't actually associate with each other. So this guy right here, circular, but 4 electrons. Circular, but 2, 4, 6, that lone pair as well. This will be 8, and this guy right here is 16. I think. 2, 4, 6, 8, 10, 12, 14, 16. Yep. So again, all of these ones, if you make an anti-aromatic molecule, these end up becoming way more reactive than their typical aromatic counterparts. The last category is what we call non-aromatic. These are just normal resonance type structures. These ones are sort of in the middle, and an example of it is a molecule like this. So here we have 2, 4, 6, 8 electrons. That kind of looks like we're doing the 4n where n equals 2. The only thing that saves this one is, yes, you have a ring. Yes, you have all p centers around it, right? We have all p orbitals around it. So it could become anti-aromatic. The one thing that this molecule does, because of its flexibility, it can avoid that consequence, that anti-aromatic consequence, just by doing a ring pucker. It ends up flipping itself up like a boat. We basically violate this case here. By doing that ring pucker, it's no longer totally planar. By being not planar, it's kind of like biphenyl I showed you at the beginning. Yes, the electron count looks like it's anti-aromatic. Yes, it's all planar. Yes, it's all sp2. But how it avoids that consequence of super high energy is just by flipping the ring, bending it, and what it means is now you kind of have an isolated double bond. You actually are breaking up or sacrificing some of the extended conjugation in order to give you back the stabilization. Yes? Yeah. Again, you don't get to choose. Like, it's not like, remember, when we talk about this hybridization, that's like saying, but I don't like drawing that resonance structure. Sorry, man. All we're saying is if you try to make that molecule, it has, because of this, the ring planarity, it might do something like what you see here. It's possible that if this thing's going to be pulled into existence, it might do this, where it sort of puckers up or it folds up one side. Then, yes, it stays sp3, then you're happy. But the molecule, because of that flexibility, it's almost like it's baited into it. It's like, hey, I got this lone pair. Can I borrow it? Yeah, no problem. Oh, no, what a terrible decision I have made. So again, something like the molecule, don't personify it that far. Molecules can't choose to be sp2 or not. So these are our 3 categories. We have aromatic, anti-aromatic, non-aromatic. Those are the 3 sort of buckets that we're trying to talk through. Now we can use this because molecules like this, if we start off, this is just a normal hydrocarbon that has double bonds. Is that, when we start off this, do the rules. Is this molecule aromatic or non-aromatic or anti-aromatic to start off with? If you had to describe this to begin at the very beginning, we have a ring. We have 6 electrons. We have sp2 all the way around the ring, but here we have sp3, right? We have a hydrogen extra there, which what that's doing is it's tying up that p orbital. But what I can do is I can start off with a non-aromatic molecule. It's just, there's no full conjugation in the system. I can take this non-aromatic molecule and I can actually become aromatic as long as I remove one of those hydrogens. So if I come along with a base, and I pick off this proton, oops, other way. So base grabs that proton. What am I doing? Not base, this is hydride. Yeah. H minus has to lose. If I depart with that hydrogen to leave behind a carbocation, what I just did is, now I'm a cycle. Remember, carbocations are sp2 hybridized. If a carbocation is sp2 hybridized, I just have a vacant p orbital at this center. So what I now have is 6 electrons. This guy here is now sp2, as is the entire ring. What I just did by taking that hydrogen and ejecting it as a hydride, throwing away that H minus, I created a carbocation that which is very, very much more stable than a normal carbocation would actually be. So basically what I can do is I can modify the state of a molecule, taking it at starting material, and by protonating or deprotonating it, I can do a reaction which is buying in or buying out aromaticity. So guys like this, cyclopentadiene, you start this off, this is a 5-membered ring with an sp3 center at the top. This is where I can use acid-base chemistry to either leave behind a lone pair or extract a lone pair, which allows me to form an aromatic molecule. This is where basically in the end, because of structures like this, I can make anions or cations which will be either more or less stable than I would normally expect them to be, only because now they're tied to an aromatic structure. So this is also a problem that we run into in terms of basicity. If you look at a guy like this, here we're taking pyrrole, it's the 5-membered ring, aromatic molecule, and pyridine, 6-membered ring. If you do the count on both of these two guys are aromatic, right? They are flat, they are cyclic, they have sp2 centers on each center, and they both, pyridine and pyrrole, has 6 electrons in their pi system. So if you had to look at these two and rank left or right, which side is more favored? Which side is more stable? Take a moment, discuss it with the person next to you. Why do you think it's left or right, and what's your rationale? What are you using to basically say which cation is more stable? Either way, you got to do something to get away from that point. I probably would remove, but okay. So the parent question is, which side or which way does the equilibrium lie? What we're trying to say is, which is the stronger acid, which is the stronger base. We're trying to identify stable materials and move towards that one. So first question, red cation versus green cation. So protonated pyridine versus protonated pyrrole. Which is more stable, red or green? Okay, green is more stable, which means red is less stable. So this is less stable or more reactive. If that's the case, the equilibrium is going to what? Move towards or away from the red species. It's going to move away from that towards the more stable species. This is more stable. Why? Well, not why does it move towards the more stable. Why is green more stable than red? Yeah.
In the case of red, you're disrupting aromaticity because you're getting the p orbital.
Exactly. So I started off with a lone pair here. That lone pair, remember, where is that lone pair? In a p orbital or an sp2 orbital? Do I need that lone pair to make a double bond that I don't yet see? Yeah, which means that guy is in a p orbital. The green one is in sp2. It's sticking out orthogonal from the ring. The nitrogen already has a pi bond. I don't need to borrow that lone pair to make my pi bond. They're both aromatic. The consequence is, if I steal this lone pair to make a sigma bond, pyridine's like, go for it, bro. I'm okay. That one's available. No problem. You come along to this molecule and say, hey, can I have that $5? And they are just in line for the coffee they've been waiting for all day. The answer is heck no, right? By stealing this, what you just did is you've localized that lone pair into a sigma bond. I've taken the lone pair, which used to be part of a resonance system, and now what you did is say that lone pair is fixed. It is bonded to that hydrogen. I've broken aromaticity. This is not aromatic anymore. This guy still is. Your pyridine cation is still an aromatic molecule, still 6 electrons, still planar, still everybody sp2. We've changed the hybridization with pyrrole, and we've broken it up so there's only 4 electrons. It's not sp2 anymore. So this is not aromatic. We've actually sacrificed aromaticity. So this is the property we're going to start talking about in this chapter now. What we're doing is not only identifying where aromatic is and not, but we have to come to this concept where aromaticity, especially with things like heteroatoms, it's a concept I can borrow, I can induce, and I can temporarily disrupt in order to do other chemistries. The important thing is, by disrupting aromaticity, you make a molecule that's one step away from something that could be super stable. We can use that to our advantage. I can take a molecule that was aromatic, I can bump it away from being not aromatic or even anti-aromatic, and what that makes it want to do is get back to aromaticity and do chemistry that's a lot harder to do normally. So this is where we can use this but to our advantage. So now we're going to talk quickly about phenols. Now phenols are aromatic molecules, benzenes, with an OH. To be a phenol, really what we're talking about is this core structure here, right? It's just benzene with a sigma, with an OH attached to it. So they're kind of like alcohols on their own. Remember though, we talked about phenol a long time ago. If I drew the tautomer of phenol, so the tautomer of phenol means I'm going to take the hydrogen from the oxygen and I'm going to promote it down to the carbon adjacent. I can redraw phenol as the ketone structure where I have my hydrogens over here. Now again, preference says if it's phenol, drawn as phenol, that's an aromatic molecule that's far more stable. This is the enol version, right? In the core, what I'm saying is this piece here is basically like an enol. You have this characteristic. Why that matters is we can use that keto-enol tautomerization, that enolate-like character, to do other chemistry as well. In general, if you look through these molecules, look at the general pKa's. So we have our meta, our para compounds where we have a chlorine attached to them. On the other side, we have our meta, para compounds with a methyl attached to them. If you look what happens to pKa here, you see a trend. Adding chlorine to these molecules, pKa goes down. Why does that seem like, does that make sense? I added a chlorine to the molecule, pKa of this molecule drops. What's going on there? Yeah, like first of all, phenol on its own. Remember alcohols, typical alcohol pKa is 15, 16, something like that. By taking that molecule, phenol, the alcohol, and being part of an aromatic ring, I've just dropped it from 16 down to about 10. What I'm saying there is the negative charge that I am generating, the O minus, is stabilized by having this resonance structure nearby. I'm more stable than your typical alcohol on its own. That's the first one here, is that having this aromatic ring is imparting stability to what might be the conjugate base. Okay, so if I'm making an O minus, adding an electron withdrawing group to that one helps me more. More importantly, look at the two patterns here. Meta and para has differences in how much they help. They're both chlorine, so why is it that para-chloro goes down a bit, but meta-chloro goes down even further? Why is that happening? Distance, yeah, exactly. This is where, remember, walking out of center means that having the chlorine closer to where the negative charge is happening up here helps me out more. That's just induction. That's moving it closer to a center. So what this is telling me is, first of all, electron withdrawing groups help. Awesome. And if electron withdrawing groups help, the closer that electron withdrawing group helps, the more it can help. That's through the inductive skeleton. We're not talking about resonance primarily. That's what we're saying is that chlorine is really interacting in an inductive capacity. Over here, we see the opposite trend. Meta and then para. Okay, so why is that happening? Why does methyl push it the other way? Methyl is a donor or withdrawer? Hyperconjugation, right? So because now methyl is going to be a donor, what's going on here that, well, but dude, this is a donor and it's closer and it's bad, but donor and further, the 4 position is worse. What does that say? Yeah?
My guess is that if you have it para, it's a lot better able to stabilize the positive charge that OH would get upon protonation.
Positive charge by protonation. Remember, this is negative, right? We're deprotonating this as acting as an acid. So other direction. No, this is it. This is important. Remember, what we're saying is the pKa is bad here because the negative charge we have here is somehow unusually mad compared to the other. It's not distance anymore. This is resonance. What we're separating out in these two is being in the meta position versus para, absolutely, closer, further. And that pattern you see here, this electronic pattern, says induction matters most for chlorine. Remember, we said methyl is a donor because of hyperconjugation. Hyperconjugation is doing what? I'm dumping electrons into what? Am I in the sigma skeleton or in the pi skeleton? Pi skeleton. The second you start talking about resonance, resonance has a different point. It's not just geometry. What we're saying here is this is probably induction, and what you'll see is in the para position and the ortho position, resonance matters more. This comes down to the relative positioning, and this is going to be a key factor that we're going to start doing as we work through these different structures. You see a similar thing with this. Remember, nitro, strong electron withdrawing group, but now look at this. Nitro meta versus nitro para, well, that did a phenomenal job. We dropped it by like 2-3 orders of magnitude. So what this is telling me is, okay, yes, electron withdrawing matters. That's between phenol and meta nitrophenol. But when I put it in the para position, even though it's geographically further, it's doing something that is really helping out. And that sort of indication, this para being way better for that sort of stabilization, is usually a hallmark that somehow resonance matters more than induction. That's what's going on here with this kind of point. If distance is not the thing that's helping me out, there's got to be something about the special positioning that does. And this is going to be the resonance structures we're going to talk through in the coming slides. Now, what you can do with phenol? Well, phenol is on its own, remember it's enol-like, so you can do some of the same chemistry that enols can do. The other thing too, because of its relative acidity, I can treat it with a base and I can use it as a nucleophile. I can turn my oxygen into an alkoxide between those two. So what I can do is prepare these kinds of systems. All right, guys, I will see you guys on Friday. We'll talk through these reactions.
Okay, so for doing these questions, the molecules here we're trying to address if they're aromatic. Remember, they have to meet the 4 rules we said. So first of all, this one, it would be classed as not aromatic, mainly because there is an sp3 carbon here, and it also doesn't have 4n+2 electrons. This one has 2, 4, 6 electrons in a cycle. However, once again, there's an sp3 center, so not aromatic. This molecule, there's only 4 electrons, so that's violating the 4n+2, but also, once again, there's an sp3 center right there, so no, it's not aromatic. This molecule has 2, 4, 6, 8, 10, 12, 14, 16. 18 electrons, which is equivalent to 4n plus 2, where n is equal to 4, so 16 plus 2. So that checks out. It's in sort of a large macroscopic ring. Each of the centers in the ring is sp2, and there's also a planar structure. This entire molecule, since it's all sp2 all the way around, will be planar, so this one is yes. Okay, now for this one, we're trying to identify what orbital each of the lone pairs occupy, and we're going to focus on the ones in the on the nitrogen, so around the rings. So we have lone pair here, 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 and here. Now, in each case, what you can do is sort of look at the lone pair, look at the bonding you currently see at the nitrogen. Here we have 1 pi and 2 sigmas. That makes the lone pair in the sp2 orbital. Again, what I'm really identifying there is the nitrogen as drawn currently has a double bond, so it means it does have a p orbital. It's using that p orbital to make this pi bond you see here, meaning that the lone pair doesn't have to be reserved to make a pi bond in a different resonance structure. Similarly, we have 2 sigmas and a pi. Since I already have a pi bond, this one also is an sp2 orbital. Here we have, again, 2 sigmas and a pi. That means it's in a sp2 orbital as well. This last one's different. Here we have sigma, sigma, and sigma bond. We have 3 sigma bonds. The lone pair over here will actually be needed to make a resonance structure. If I use a resonance structure, something like that, that's how I make my pi bond. So at the moment, this guy is in the p orbital. Again, we're looking at that 2 ways. There's currently not a pi bond as drawn in this Lewis structure, and we have to use that lone pair to make a resonance structure that does create a pi bond. Now, the second one's over here. We have nitrogen lone pair and nitrogen lone pair. Of those 2, both of them are sigma, 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 and over here, sigma, sigma, sigma. So in all these cases, once again, there isn't an existing pi bond, so it's not immediately obvious. Instead, what we can do is make a resonance structure, something like this, where I'm donating that lone pair down, which means it is reserved in the p orbital in order to make a pi bond in some resonance structure. Same thing here. In the second one, I can draw a resonance structure where I'm donating it down to make, let's say, a pi bond, ejecting out here. So again, this is going to be in a p orbital. Now down here, these 2 nitrogens, we have lone pair, and this lone pair out here. So again, looking at the constituents, the lone pair at this side, sigma, 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 that one is going to be in the p orbital, sigma, sigma, and a pi bond. This is in the sp2 orbital. This one here, we have 2 sigmas, 1 more. This one will actually still be in the p orbital because that lone pair can donate down to make a resonance structure out here. One quick note about aromaticity. Yes, this lone pair is in the p orbital, but it is not counting towards the number of electrons around the ring in this core center. As we discussed, I have a lone pair here, here, and here. Those core 6 electrons are what are available for doing forming a resonance structure that is an aromatic molecule. These 2 out here are not part of that. We're just stating that they would still be hybridized as a sp2 center because of the resonance structure that's possible, but they're not part of the count when we're talking about making an aromatic molecule. So if you look at each of these and we're saying how many electrons, pi electrons, would I either have to add or remove in order to make these compounds an ion that is aromatic. In other words, we can charge them in some way to make something that gets to an aromatic compound. And then what would the overall charge of the aromatic ion be? So in this case, we have 2 and 4. There's only 4 electrons. That would be either, if we did 4n plus 2, where n equals to 1, we were trying to get up to 6 electrons total, so we need to have 2 electrons available here. Now, the way we could potentially do it in this case is I have these protons, if I used a base that then deprotonates the center and leave those electrons in the molecule, so make a carbanion at that center, that deprotonation would now give me my cyclopentene like this, with a lone pair and negative charge on that carbon. This now has 6 electrons, and this is an aromatic anion in this case. Now, in the second molecule, we have 2, 4, 6, 8 electrons, and that gives us 8 electrons, which doesn't match our 4n plus 2. So what if we were to add 2 electrons to the system to give us a total of 10? So that would be through a reaction like a reduction, where we might add, let's say, potassium metal, which is actually, you can think of it as potassium plus and an electron minus. So if we had 2 equivalents or 2 moles of that per one of these starting materials, what we could generate is something we've injected 2 electrons into the system. So that might be looking like a lone pair here, negative charge, double bond, lone pair, negative charge. So this is a total of a 2 minus charge overall, 10 electrons in a ring, where because these are drawn, even though they're localized, these are in resonance. They will actually be an aromatic molecule because of that. So it's a very strange aromatic dianion.